Welcome. This is an interesting problem at your screen, and you might have solved this problem previously, and many people will be familiar with the famous trick they apply to solve this problem. But somebody might don't know this, so I'm going to teach them that particular technique. So read the statement of the problem first. It says water flows out of a vertical open-topped, an atmosphere of course, cylindrical vessel through a hole at the bottom. You can recognize all the things, and find the rate of change of height of water surface, water level, in terms of instantaneous height h. That's the clue. Measured from the bottom. I guess h is this height, and if half of the water flows out of the vessel in time t, how long will it take for the vessel to be completely empty? That's a good question. It has been frequently asked to the students. So before going to solve this problem, we must formulate few things first. Let us denote the cross section of the interior of the vessel by A and the cross section of the hole by A naught, and the continuously varying velocity of the water level by B. It's always variable, it's always varying, it's always changing, and velocity of water flowing out of the hole by capital V. And so what we are waiting for, we can use the Bernoulli and its brother equation, the equation of continuity, equation of conservation of matter. And to apply the Bernoulli's theorem, we have taken 2 points. One point is here and one point is here, and we can apply the Bernoulli's equation for this ideal fluid flow. And I can write simply here at A, the velocity is v, so I can write kinetic energy per unit volume as half rho v square, plus pressure there is P naught, atmospheric pressure, and I can use this level as the reference level for writing gravitational potential energy per unit volume, so that I can write here rho gh, and that will be equal to the kinetic energy per unit volume of flowing out water as half rho v square, plus pressure energy per unit volume is P naught, and rho gh here is 0. So this is our Bernoulli's equation, and without any delay we should write the equation of continuity, also the law of conservation of matter, and that is written in form of rate of change of volume of liquid. And so at the top it is V multiplied by A, and at the bottom it can be written as V A naught. And we can use these two relationships to find out the velocity V, the velocity of water level. And you can get here something like you can get here velocity at this height h as under root a naught square divided by a square minus a naught square 2gh. Rho must be cancelled out, and I could write it like something like I could have written it like 2g dash h. So what do you think will be the value of g dash? G dash value is what? This g dash I get something. This g dash you can write here as uh, a naught divided by under root, and I am doing nothing, a square minus a naught square multiplied by g. And it seems like the water, the liquid, is traveling in an artificially created gravitational field. Of course, this time vertically downward. And you can see one more feature of this G-dash thing, that there nothing changes in it, in neither a naught nor a nor g, so everything constant here, so we can consider it a constant. So we can write here that v is directly proportional to under root h, that the rate of change of height of the liquid surface is proportional to the square root of the height. And yes, it is my take from here. So we just solved the first part of the problem, but I'm going to solve the next part of the problem as well. And to solve this problem, first I will take the total height of this cylinder, of this vessel, as capital H. That the initial height of the liquid surface relative to the bottom of the vessel is capital H. And you can see this height is right now h minus h. And I'm going to consider a weird thing, quite weird thing, and this is the trick. Now I'm not going to solve, going to analyze the velocity of liquid or whatever, or water, whatever it is, but I'm going to consider the motion of a weird object. I will not consider its mass. It's a point object, point-like object, a particle. And I have provided it a velocity v naught in this direction, and this value of v naught I could take as under root 2 g dash h. Yeah, and it is moving in an artificially created gravitational field in vertically upward direction. And acceleration due to gravity in this artificial gravitational field is g dash. Why would you like to do this? Why you will do this? I can do this. I am doing this. It's my will. What is the benefit of doing this? You can ask me. And well, I think in this field, if it travels the height h minus h and reaches to this point, it will have a velocity v that will be exactly equal to this v. How? Yeah, well, let me solve it. And to solve it, let me use the work energy theorem. And I can write here the final kinetic energy simply as half mv square minus initial kinetic energy at half mv naught square. M is the mass of that object that is going to be cancelled out, equal to work done by the artificial gravity on it. So it will be mgh, but it will be negative because the gravitational forces acting on this particle in this gravitational field g dash is in vertically upward direction, and it is moving in vertically downward direction. So the work done by gravitational force will be negative, and it will be mg dash, and the height it lowered h minus h. And now you can simply cancel out m and write down v naught, the value of v naught, and you will get v square by 2 minus this thing, half V naught square is 2 G dash H, and you will get minus G dash H plus G dash H, and you can see you can cancel them both, and now you got what? V equals under root 2 G dash H. We just obtained this value, and this value is same. So you can work on this tiny particle in this gravitational field rather than thinking about the water lowering and the flow of water, flow of liquid. So I'm going to solve this now. I'm going to solve this, and what next? To solve the rest of the problem, and I'm going to write that the rate of fall of the water surface at time t is the speed of this tiny particle moving in a weird gravitational field, and I can write its velocity at time t can be written as v naught minus g dash t. And I also know that when half of the water has flowed out, the small body has reached to a height h by 2, capital H by 2. Bole, how do you know this? Because I know this equation, and I will know that if I write Vh in terms of h, and I can write V dash h by 2. Remember, I'm talking about the moment when half of the water has flowed out. Then that means the height of the water column that was initially h has now lowered down to h by 2. So I know that when the half of the water has flowed out, the small body reaches a height h by 2. A small body has been lowered by a height h by 2, and its velocity will become under root g dash h. So I can write here, for the moment I need to find out something, the time to reach, time to empty the cylinder by half, and I can write here, I got the velocity here simply as under root g dash h at the moment, and its initial velocity was under root 2 g dash h, and time we are needed to find out this is t, and you can find from here that t is equal to root 2 minus 1 under root h by g dash. You can put the value of g dash and you got the result. So time, and now we need to find the time to completely empty the cylinder or the vessel, and I know at that moment h has become equal to 0. So velocity at that moment is equal to 0, and the required time is nothing from this formula, but the time is required time. Suppose that I could write this time as t naught. So t naught is equal to v naught by g dash, and You can put the value of V naught as simply by under root 2 G dash H by J dash, and you will get the result simply as root 2 under root H by G dash. And you will see this time is root 2 by root 2 minus 1 t. T was half the time, half to empty the vessel by half. So these are the relations, and this is the solution. Try to learn these things. Thank you very much for watching.